All right, welcome everybody to the HAO colloquium. And I'm happy to introduce Supriya Dayananda, who is at the IAC in the Canary Islands. And Supriya obtained her PhD from the Indian Institute of Astrophysics in Bangalore, India, on the topic of exploration of the second solar spectrum through polarimetric studies. She's currently working as a postdoc fellow, as I said, at the IAC, which is the Instituto de Astrofísica de Canarias. And she's a member of the PolMag group there. And that is a European Research Council advanced grant project. Her scientific interests include coronal magnetometry, spectral line formation, polarized radiative transfer, and scattering polarization on the sun. So we're very happy to have you here. And welcome, Supriya, and go ahead and get started.
Thank you very much, Sarah. I will just share the screen. I hope. Okay. I hope I'm audible and you can share, you can see the presentation.
Yes, looks good.
Yes. Okay. Thank you again for this opportunity, and also thank you all for joining. I'll be talking about a new forward modeling code called Corona that we have been developing here as a part of the European Research Council Advanced Grant Project called PolMag. And this code has been developed in collaboration with all these people at the Instituto de Astrofísica de Canarias here in Tenerife, Spain. The aim of developing a code like Corona was to have a theoretical tool in the era of multiple solar coronal missions that we have, like Aditya L1, DICIST, UCOMP, and many other ground and space-based telescopes. Of course, the main idea of all these missions is to probe and understand the solar corona in a better way, and to get an idea of the dynamics which are highly coupled to the magnetic fields in the solar corona. One of the ways in which we can understand these magnetic fields, or these magnetic fields leave their signature in the coronal spectral lines by the mechanism of polarization. In corona, the radiation anisotropy is very significant, mainly due to the center to limb variation, and also because the large heights above the sun's visible surface. So there are two main types of spectral lines which can be used to probe the physical properties of the solar corona. One is the permitted lines, which are formed due to electric dipole transitions. These are the Lyman alpha lines of hydrogen 1, helium 2, oxygen 6, which are usually in the UV range of the spectrum, except for another promising diagnostic line, that is the helium 1 10830, which is in the IR. The other set of lines are forbidden lines, which are formed due to magnetic dipole transitions. These are the lines coming from the highly ionized species of iron, silicon, magnesium, and so on, which these are the lines that DICIST, Aditya L1, and even UCOMP is interested in. So if you look at the physical mechanisms that influence the formation of these lines, or in particular the polarization signals in these lines, then here I list some of the main physical mechanisms that can influence these lines, mainly talking in terms of the mechanisms which break the symmetry leading to the polarization signal. The first important mechanism is the anisotropic illumination. Like I said, it leads to scattering polarization or atomic polarization. Whenever the atoms in the solar corona sees the radiation from the underlying layers, which are anisotropically illuminated, then the magnetic sublevels of these atoms are unevenly populated, leading to scattering polarization. The other important mechanism is the magnetic field itself. The magnetic fields manifest itself both in terms of Zeeman effect and also Handley effect. If you look at the ratio of Zeeman splitting to Doppler width, which is supposed to give us an idea of how sensitive the line is to Zeeman effect, then you see that this ratio goes directly to the magnetic field strength and inversely to the square root of temperature. So in corona, since we have very low magnetic field and very high temperatures, this ratio is generally small, or in other terms, like the coronal lines are not very significantly sensitive to Zeeman effect, except of course for the IR lines, mostly the forbidden lines, which have very large wavelength and hence can show some sensitivity to Zeeman effect. The important diagnostic tool that we have to understand magnetic fields in the solar corona through polarization signals is the Handley effect. Handley effect is the modification of the scattered polarization signal by the external magnetic field. These fields change the atomic level coherences, usually resulting in depolarization and rotation of plane of polarization. And a line is said to be sensitive to Handley effect when the atomic level splitting is of the same order of the natural width of the level. So with this condition, you can get an estimate of critical magnetic field, which would say the field strength for which the line might be sensitive to the Handley effect. And usually, once you know this critical magnetic field, we can say that the line would be sensitive to the field strength of 0.2 times this critical magnetic field to 5 times of this critical magnetic field, in that range. So if you look at some of the lines, for example, Lyman alpha line of hydrogen, then it has a critical magnetic field of 53 Gauss. You see that this critical magnetic field expression is inversely proportional to the lifetime of the level involved in the transition, or you can say it is directly proportional to the radiative transition coefficient. For the Lyman alpha line of hydrogen, the radiative transition coefficient is quite high, that is around 10 power 8 per second, and it gives a sensitivity of 53 Gauss for the Handley effect. Wherein, if you take an example of forbidden line, that is 10747 line of iron 13, the radiative transition coefficient for this line is very low, or in other terms, the levels involved in the transition of this line is very long-lived, and this long-lived levels gives a sensitivity, very small sensitivity to the critical magnetic field strength for the Handley effect. You are talking in terms of 10 power minus 6 Gauss or something like that. So what it says is, by probing different lines, both permitted and forbidden lines in the solar corona, you can in turn probe the magnetic fields across a wide range of magnetic fields. So the other important mechanism which can break the symmetry and change or result in the polarization signal is the solar wind velocities. Basically, the atoms in the solar corona will experience different intensities coming from different directions because of the solar wind velocity and hence the Doppler wind, resulting in symmetry breaking. So this symmetry breaking can in turn lead to the polarization signals. I will talk about examples of this and applications of P corona exclusively in this context in the second half of the talk. So the next physical mechanism is the collisional transitions. In solar corona, for some of the lines, mainly forbidden lines, since the atomic levels are long-lived, or if since the radiative transition coefficients are very small, the collisional transitions can be in comparison to the radiative transition itself and have a huge impact in populating the atomic levels and also changing the atomic orientation and alignment. Hence, collisions become a very important factor when you are looking at especially the forbidden lines that are formed in the solar corona. Apart from these, the active regions on the photosphere can also break the symmetry of the radiation that is coming from the underlying layers and can lead to the change in the coronal line polarization. So the idea behind peak corona was to include most of these physical mechanisms and to have a forward modeling code with them to model both permitted and forbidden lines in 3D models of the solar corona. So P corona, the P here stands for the project name Pullman, new region in the solar corona. So it takes into account anisotropic radiation, Hanley and Zeeman effects, and also collisions and solar wind velocities. We do not include the effects of active regions on the photosphere yet, but the studies by Lee et al. And Sharon Dima in 2021 have shown that these effects are not very significant and will not lead to a significant error in the measurement of polarization signals. So let's look at the code P corona itself. Like any other forward modeling code, P corona consists of 3 important parts. The philosophy behind a forward modeling code is you supply a set of input parameters to the code and you solve statistical equilibrium equations or the equations which account for all the physical mechanisms that you're talking about. And then you get your emission coefficients, which should tell you what your Stokes parameters would look like. So now I'll try and explain each of these blocks in the context of P corona, what goes in and what exactly we are accounting for in P corona, and also try to distinguish at the places where it arises, the differences between permitted and forbidden lines that you should be mindful about when you are doing forward modeling. So let's start with the first block, that is the input parameters. There are 3 main input parameters that goes into P corona. The first one is the atomic data itself. So here is where you specify all the quantum level information of the line that you're looking at, like the different levels and their total angular momentum quantum number, Landé factors, radiative transition coefficients, collisional transition coefficients, and everything that comes as a part of the atomic information that you want to model, the line that you want to model. So for a permitted line, the atomic model is fairly simple because these lines are generally not very strongly affected by collisions, and a simple 3-level atomic system like that is shown in the left panel would be sufficient to model these permitted lines. This is an example for the Lyman alpha hydrogen line. Whereas for forbidden lines, like I told you, the levels involved in the transitions are very long-lived. So on the right panel, this is an example case for iron 13 model atom. So if you look at the 10747 line, it is basically coming because of the transition between these levels. But since these levels are so long-lived, in that duration, the radiative and collisional transitions from other upper levels can change the population and other atomic parameters of these lines, which can in turn change your polarization signal. So hence, an accurate multi-level atomic system becomes very important, especially when you are dealing with forbidden lines. All the atomic data in P Corona comes from Chianti, the latest model of Chianti that is available. So the next input parameter is the incoming solar radiation as seen by the coronal atoms. For forbidden lines, which are in the IR, it's fairly simple. It's the underlying emission is usually in the continuum, like here in the right panel. But for the permitted lines, you should be mindful about the strong emission profiles most of these lines exhibit from the underlying layers. So in the left panel, this is the hydrogen Lyman alpha line emission computed using RH code. And this line forms somewhere in the upper chromosphere and transition region. And the coronal atoms sees this emission as their incoming radiation. So the third input parameter is the solar coronal model itself. This is where you specify the temperature, electron densities, magnetic fields, and velocity fields for which you want to forward model the line for. In P Corona, we have tested the code for two specific models. One is the one coming from predictive science group, large models going up to 2 or 3 solar radius or even higher if you want to model them. And the other set of models we have tested for are the numerical simulations from MURAM for different solar conditions. Though we have tested the code for these specific models, the code is written, or we have tried to write the code at least in as general format as possible, so that if you have any other atomic or atmospheric model, then as long as you are supplying them to the code in the specific format that we give, then you can basically use any of the atmospheric models and atomic models to get results from P Corona. I'll talk about these towards the end of the talk and show you some the examples and the documentation we have on these input parameters. So once you have these input parameters, you solve statistical equilibrium equations. The theoretical formulation that we follow is the density matrix formalism that is given in detail in Landy and Landolfi book. What happens at this stage is you have a set of equations for radiative transitions and collisional transitions, and you solve for these density matrix elements called ρKqs, which contain the information about the atomic population, orientation, and alignment. So if you look at these equations for the radiative transitions, it contains the transfer and relaxation rates for the processes of absorption, spontaneous emission, and stimulated emission. What in turn goes into computation of these rates are what is called your radiation field tensors, which are nothing but the tensors containing the information about the geometry and the intensity of the incoming radiation. So here in the expression for JKQ, you see the intensity. Now, when there are solar wind velocities present and can have Doppler effect, either Doppler dimming or broadening, then it is accounted here in this radiation field tensors. Likewise, the collisional transitions, these rates are in turn dependent on the electron number densities and temperatures that is coming from the model based on which you calculate these collisional coefficients. So once you solve them, these statistical equilibrium equations, and you obtain your density matrix elements, you simply plug them in here in the emission coefficients, which tell you the emission for the particular Stokes I, Q, U, and V. Though this looks complicated, it is simply made of an absorption term and the atomic information that is of different magnetic substates, and the TKQs are the geometrical tensors, which contains the information about the scattering event, and rho KQs, like I said, are the atomic level informations and the profile function. So once you compute these emission coefficients, taking advantage of the fact that corona is optically thin, you integrate these signals along the line of sight, and you have your Stokes parameters. So this is what happens in peak corona. And here is an example after doing all these computations for a predictive science model. So these computations are done for a simple case when no magnetic or velocity field effects are considered. It is simply when there is a resonant scattering of the light from the underlying layers is happening, and you see an emission in the solar corona. So the left panel is one such emission predictive science model for Lyman alpha line of hydrogen, and the right panel for the same predictive science model, the emission in forbidden line of iron 13 10 47. The black lines here represent the direction of the linear polarization in each case, and you see that for a permitted line, it's always parallel to the solar limb, and for a forbidden line, it's perpendicular to the solar limb. This difference in the sign of linear polarization signal simply comes because of the change in the sign of the geometrical tensor. Like I said, this is a tensor containing the information about the scattering event. And this change in sign for the linear polarization signal is what gives you the change in the linear polarization directions. Okay. So a more illustrative example. So now let's, like I said, like in peak corona, we have tested for a predictive science and also a MURAM model. So here is one such example for iron 13 10 7 47 line. Top panel is what you get from a predictive science model going up to, say, 3 solar radius or more. The first is the intensity, then total linear polarization, and the rotation of plane of polarization. And the bottom panel, the same parameters, but in a MURAM active region model. But these are representatives of IQU. I told you we also have Zeeman effect in peak corona. And if you look at Zeeman signatures, that is maximum of Stokes V over I for 10747 line in the MURAM active region model, this is how it looks like. But both these examples here for the predictive science and MURAM models and also the Stokes V, maximum of Stokes V here, are the results that you would obtain when you do frequency integration of the signals, or like when you're comparing the imaging of the solar corona. But in peak corona, we also have an option to get the spectral variation of these Stokes profiles. Say, for example, at point P1 and P2, you would like to see how the Stokes profiles varies across the wavelength. Then you can simply choose those points in the computations and get the spectral variation. Here is for top panel is for point 1, I, Q, U, and V. And the bottom one is for a point 2 within this model. At this point, I would like to point out that in peak corona, we consistently handle the Zeeman effect without relying on the weak field approximation. What do I mean by this, and why is it important? The Stokes V, whether you are in weak field approximation or a consistent treatment, is not going to change. But once you are in the weak field approximation regime, you are missing out the effect of Zeeman signatures in Stokes Q and U. Let me show you by example. Let's switch wavelengths and look at how the silicon 9 39343 line would look like in this active region model. This line mainly because it's of the very large wavelength and hence should show more sensitivity to Zeeman effect. So if you consider a point P here for this active region model and obtain your spectral variation of IQ, U, and V, now first ignoring the Zeeman effect. You don't consider the effects of Zeeman effect, so you see the blue line which represents Stokes V to be 0. Switch on the Zeeman effect, you see a very strong, nice Zeeman signal. Along with that, notice the green and the orange line, which is for Q and U respectively, also showing the signatures of Zeeman effect. This is what I mean. You will lose these changes in the signature or the contribution of Zeeman effect in Q and U if you are in the weak field approximation regime. Of course, if you move to a higher point in the model where the magnetic field effects are very low, then you need not have to worry about it because then your contribution to Stokes V through Zeeman effect itself is low. And now you compare the Q and U signatures with and without Zeeman effect, and they are more or less the same. Before moving on to the application parts of P Corona, I would like to highlight here some of the advantages of having a forward modeling tool like this. The first one is it allows you to make a direct comparison with observations. So if you can generate synthetic profiles from the forward modeling code and compare them with the observations and evaluate the accuracy and consistency of the atomic and atmospheric models you're using. And the next advantage is you can do a range of parameter exploration. That is, by adjusting different input parameters, you can study how the signals or the Stokes profiles are sensitive to these input parameters and have a better idea of different physical processes and their impact on the Stokes profiles. You can do a model validation and refinement by again comparing the results of observations with the synthetic profiles. By here, when I mean the model here, I'm specifically referring to the atmospheric models. This was recently done in Shad et al. Paper, where they presented the first decreased observations. They compared two models of the predictive science group, which are coming because of considering different heating mechanisms, and compared them with the observations to see which of those models gave them a better fit. So it's the forward modeling tool which gives you an advantage to do this, especially now when you have a huge number of numerical simulations of the solar corona. You can validate them by using the synthetic profiles and comparing them with the observations and have a better understanding of which of the numerical simulations are giving you a better results and why. And the other important advantage is you can use forward modeling tools to design better instruments. That is, you can compute how different signals are going to respond to different instrumentation conditions and get an estimate of quantities like exposure time and basically have a better judgment of the kind of observations and the instruments that you would need for the observations. So now I would like to talk about some of the applications that we have obtained using P-Corona. The first results that we obtained using P-Corona were by studying the Lyman alpha lines of hydrogen-1 and helium-2 and exploring their use to probe solar corona to understand the Handley effect or the magnetic field impact through Handley effect on these lines. These two lines were of specific interest because these Lyman alpha lines are sensitive to Handley effect in a huge range of magnetic field strengths. So the hydrogen line has a magnetic field sensitivity of 53 Gauss, and the helium-2 line has a sensitivity of 850 Gauss. So the idea was, of course, for the kind of field strengths that you see in the corona, you shouldn't see any sensitivity through Handley effect in helium Lyman alpha lines, whereas you can expect the Handley effect signatures in Lyman alpha line of hydrogen. However, both these lines have a strong emission profile from the underlying layers. So the left panel is what the hydrogen Lyman alpha line, and the right panel is the helium Lyman alpha line from underlying layers of solar corona. Since there are strong velocity fields in the solar corona and a narrower helium emission line, we expected to see this helium-2 line to be affected by solar wind velocity, probably also the Lyman alpha line, but then the idea was to see to what extent the solar wind velocities affect both these lines, and will that be of any restriction for us to use the helium Lyman alpha line as a reference line to understand the Handley effect or magnetic field sensitivity in hydrogen Lyman alpha line. So for these studies, we considered two sets of predictive science models. One we called the magnetic model. In this model, we chose this specific model because of the strong magnetic fields that we saw in the model. And the second model I'll show later is called the dynamic model, which had strong velocity fields in that model. So in the magnetic model, which is correspondent to Carrington rotation 2157, this is from the predictive science group. Here is a sample of plane of the sky variation of different physical parameters in this model: the temperature, the electron or proton densities, the magnitude of magnetic field. You see close to the surface in this region, you see even magnetic fields going up to like 50 to 100 Gauss. And here is a representation of plane of the sky. In the plane of the sky, the magnitude of velocities. This is just plane of the sky representation. Of course, in P-Corona, all the calculations are in 3D. You have all these physical parameters at each point in 3 dimensions in the model that you consider, and you solve statistical equilibrium for equations for each of those points, and then you integrate the signals along the line of sight to obtain your final Stokes profiles. Okay, before we moved on to the computations, first we calculated the number densities of both hydrogen-1 and helium-2 for these coronal conditions that the model is providing using the ionization fractions and abundances from Chianti. So this is how the number densities of hydrogen-1 look like. And if you look at the helium-2 number densities, this is how it is. I'll just toggle between these slides to show the kind of variation of both the number densities of hydrogen-1 and helium-2. And you see that notice the color scale here. The bluer it is, blue to green it is, the numbers are going up. So the hydrogen number densities are much lesser than that of helium-2 number densities. Obviously, because if you look at the ionization fraction for these two, then the helium-2 ionization fraction is for the coronal temperature, say for 1,000,000 degrees, is around 10⁻⁵. But if you see for the hydrogen, then it is for the 1,000,000 degrees, you're talking about 10⁻⁷. So this difference in the ionization fraction, of course, is resulting in the number densities as well. Then we calculated the intensity in both these lines for this predictive science model. So here is the intensity of the Lyman alpha line of hydrogen in the predictive science model. And then here it is for the helium-2 line. Again, notice the color scales. And you see that there is more emission of hydrogen than helium. But the explanation for this, for a better comparison, okay, before going there, let's take a 1D cut in the model. So basically, I'm now looking at a 1D variation from the surface along this direction going up to 3 solar radius. Just for an easier comparison, here in the left panel, you see like I said, there is more helium-2 than hydrogen-1, but in the intensity, you see more hydrogen-1 than helium-2. This is simply because the coronal atom sees more hydrogen emission from the underlying layers than that of helium, which is directly reflected in the intensities. So once we have these intensities, you notice that as you move, as expected, as you move higher and higher in solar corona, these intensities drop down. And the question was whether we will be able to measure these kind of intensities, or what kind of integration times would you need in order to detect these signals. So to get an estimate, we did a simple calculation using this relation. Say you have a telescope with 25 centimeter and with 20 arcsecond resolution and 1% instrumentation efficiency, and you want to detect of like 10⁻⁷ photons, then what are the kind of exposure times you would need? So that is what we calculated here for both these lines. Again, let's make that 1D cut to understand them better. Then you see here that the y-axis is the exposure time in minutes. And as you go somewhere above half a solar radius above the surface, you are talking about more than an hour of integration time for helium-2 line. Solar corona is very dynamic, and you might lose all the information that you're looking at in these kind of integration times. So for all the further calculations, we just restricted ourselves to just half a solar radius and did our linear polarization computations. Okay, so now let's see how the linear polarization signal looks like in both these lines. So here, again, the first case, I don't consider any magnetic field or velocity field effects and compute how the linear polarization would look like. And you see that both the Lyman alpha lines give you the exact same behavior. This is simply because both these lines come from the same kind of atomic transitions, that is 3½ to ½ transition, and hence the total linear polarization signal in the absence of any of the external factors would look exactly the same. So now let's switch on these external factors. Now let's include the effect of magnetic and velocity fields. And what do we see? So in the left panel, what I plot here is the relative polarization. That is the change in the polarization signal with respect to the case when there were no symmetry breaking effects, that is the magnetic and velocity fields. So in the right panel, it is the rotation of the plane of polarization. So this is the relative polarization and rotation of plane of polarization for Lyman alpha line of hydrogen. And and you see that there is significant relative polarization close to the surface here, going up to something like 20%. And this is purely because of the strong magnetic field in those regions that are present, a clear signature of Hanley effect in this line. This particular signal, and correspondingly the rotation of plane of polarization in those regions. Now let's see what happens in helium-2 Lyman alpha line. You hardly see any relative polarization or also rotation of plane of polarization. There are some signatures, but now it is important for us to understand whether it is coming from the magnetic field effects or velocity field effects. Mind you, we shouldn't get any of the magnetic field effects for the kind of fields in the model for helium-2 Lyman alpha line. So just to make it clear, now in the same model, I forget about the velocity fields, do the computation only for magnetic field effects. And for Lyman alpha line of hydrogen, you have the relative polarization and rotation of plane of polarization. And for helium line, there is nothing, proving that the effects of Hanley effect are not there in helium Lyman alpha line. Now let's just include the effects of velocity fields. A much broader Lyman alpha line of hydrogen from underlying layers will be very less sensitive to the kind of velocity fields in the model. That is what you see here. There is no change in these quantities. And in helium-2 Lyman alpha line, you see some changes, but not very significant. So to rule out, or to understand better to what extent these velocity effects are there in helium line, we considered another model. This was our magnetic model. And in the regions that we are looking at, you see the velocity fields are somewhere between 50 to 100 kilometers per second or less. So we considered another model, which we call as the dynamic model, in which there are velocity fields close to the surface, even going up to 300 to 400 kilometers per second. So let's repeat all these calculations with this dynamic model and see what happens. Case 1, only magnetic fields. You see, again, in this model, there are some magnetic fields in these regions, not as strong as in the magnetic model. And those magnetic fields leave their signature in Lyman alpha line of hydrogen and nothing in helium. And the interesting case of the velocity field effects only, then you see that these velocity effects are not very significant in Lyman alpha line of hydrogen, but in helium line, it's very, very prominent, as if it is mimicking the symmetry breaking effects that might have come because of the magnetic fields. So to conclude this part of studies, the idea was to explore whether we can use helium-2 Lyman alpha line as a reference line to study Hanley effect in hydrogen Lyman alpha line. And what we saw from our studies was, yes, you can use it as a reference line, given there are no strong velocity fields in that region. Or if there are velocity field effects, taking advantage of forward modeling, you can account for those velocity fields and you can still use helium line as a reference line to get magnetic field information from the polarized signals in the hydrogen Lyman alpha line. We extended these studies to forbidden lines. We were motivated to consider the effects of velocity fields in the forbidden lines by a comment made in the review paper by Cassini et al., wherein they say, close to the wavelength of iron 13 lines, both 10747 and 10798, there are strong silicon 1 photospheric lines which can have an impact because of the solar wind velocities through Doppler effect. So what do they mean? Here is the FTS atlas for this wavelength range. And you see the emission in 10747 and 10798. It is in the continuum as expected, but these silicon lines close to them at a Doppler distance of like 72 kilometer and 47 kilometer can have an effect on the 10747 lines because of the Doppler dimming. So basically the coronal atoms, because of the solar wind velocities, instead of seeing the intensity from the underlying layers in this particular region, can instead see this intensity. So we explored this in a series of mu-RAM simulations this time. And here we plot the magnitude of velocity in all the mu-RAM models that we had for different solar conditions. And we see that the open flux model is where you see maximum change in the velocity fields. So we consider this model for further studies. And we repeated our calculation like we did for the Lyman alpha lines by now here plotting the relative difference in intensity, total linear polarization, and rotation of plane of polarization. And we see that this is for 10747 line. And we see that the effects due to the solar wind velocities on these lines are not very significant. And they are very localized to these regions where the fields must be very strong. It can also be that these Doppler dimming effects can cancel out when you are considering line of sight integration, and because the fields are going to vary along your line of sight as well. It's the same conclusion that we got from 10798 line calculations as well. And basically, if you are dealing with these lines, then probably you can ignore the effects of velocity fields while studying the Stokes profiles or the polarization signals of these lines. Okay, this is the summary of the whole talk. I would like to mainly draw your attention to the fact that the code we have developed, P-Corona, is now publicly available with a graphical user interface. So before I stop the talk, I would like to give a demo of the things that you can do with the code. I will just stop sharing the screen and share the screen. Okay.
trying to figure out which. It might be easier to share the whole screen.
Yeah, I'm trying to do that, but I'm not able to share, unfortunately.
There's like a multi-step. You click on the share whole screen, and then you have to also click on the accept.
Now I can, yes.
Yeah.
Okay.
I keep changing it.
This is the tab. This is the Git location where you can download the whole code from. And if you go here, you can also see the link to the documentation that we have developed for the code. Just click on this. So if you go here, we have tried to put all the details in this documentation, starting from the installation of the code, the dependencies you would need, and how to compile, all those things, and how to run the code with specific instructions about the way parallelization is done inside the code. And we also give in the Git directory a simple test case for a 3-level atomic system and for a predictive science model. You can, this is a small case so that you can just run this code probably in your laptop and get the results and make sure you're running the code correctly and get yourself familiar with the code. Then if you go to the appendix, this is what I was talking about. There is a format in which we give all the input parameters to Coronal. Everything is in HDF5 format. Here we have tried to put all the details of these files. And as long as you are constructing your atomic and atmospheric file in this format, you should practically be able to run the code for that particular model. Towards the end, we have also given some basic instructions if you're not familiar to use HDF5 files and to make simple changes within the existing files if it's a 1D data and things like that. Along with that, like for more complicated examples are put here in Zenodo. So in Zenodo, we provide a set of atmospheric models from predictive science and a set of atomic models. You would see here for the different ions, mainly the thickest would be interested in, and also 2 example outputs for the kind of parameter settings that you should do if you want to do the computations only in the plane of the sky, or if you want to do computations to obtain the full profiles and things like that. And we plan to keep this updated every now and then when we have new results so that you can reproduce them using Corona and if you're planning to use. And Corona also comes with a graphical user interface, which can simply be used using Python. And like here, I will try to show you a sample example. So I have an output generated from Corona, and you can use the GUI to visualize both the input and output parameters. And once you open this window, you will see the options to plot your output in a 2D format, if you want to plot the profiles or if the lineouts. As soon as you select 2D format, you get this option. And you can choose, for example, you want to plot the intensity and just click draw. And you should have your intensity. You can do a lot of things using this GUI just to understand the results that you have obtained in a better way. Zoom in for the specific region and see how your results look like. Or for the profiles, if you want to look at how the profiles look like. Say, for example, the Stokes I at X and Y1, then it should give you that, or Stokes V for that particular region, or in fact, one of the useful things you can also do is to see if you want to draw a line out here and to see how the parameters vary. Both, like I said, this can be done both in atomic and atmospheric model. Let me put some numbers here, say at x 0.5 and 1.5 to again, sorry, x 0.5 to y.5 to x 1.5 to, and I'll call this line 1 and draw. Then, okay, you can draw the legend and also the reference line. So it will tell you, okay, in window 1, you are looking at the variation of intensity along this direction, and you can add multiple line outs and compare them. So basically, GUI should help you get a better understanding of the results that you obtain. And we have, like I said, more details in the documentation about how to use each of these windows and how to specify each of the parameters you see on the in these windows. And I hope that is useful. So I will go back to the presentation wherever I was. Yeah. And yeah, stop here.
Excellent, thank you. Okay, do we have questions? Alan, go ahead.
Hello, this is Alin Paraschif from NSO. I would urge you to consider studying the photospheric and absorption features from the Earth's atmosphere more before deriving your conclusions on the velocity argument. Because 1079 is not affected by a silicon one line, it's affected by an atmospheric water line, which is the deep absorption in that core profile. Thank you.
Okay. Yeah, that's interesting. I didn't know. Thank you.
Other questions? Yeah, who is? Oh, Momo, go ahead.
Hello. That was a really interesting talk. Thank you so much for presenting that. I have a question regarding which Chianti version did you use to compute the abundance in the coronal abundances?
For these, I think for the results I showed, it was from, if I remember correctly, from Asplund Abundances from Chianti database, I suppose.
Mm-hmm.
Yeah. Yeah.
Okay. Yeah, because I was just wondering because there was a recent paper by, well, a few years ago by Giulio Del Zana, where they, I think, included a bit more physics and showed that the helium-2 Lyman alpha should be, I think, way brighter than what was anticipated before. So that's why I was curious, how do you do that?
Yeah, for I know the paper by Giulio. It's they talk specifically the helium abundances in the context of 10830 line, and different physical mechanisms that can increase the abundances of these lines. But that was specific to helium line, and none of these lines are. But those are some things to consider and improve the forward modeling code. But for now, the computations that I showed you, it's simply one of the abundances that Chianti lists, and you just use them. Yeah.
Awesome, thank you.
Yeah.
Other questions? All right, well, since we're past the hour, I think we're going to have to wrap up, but that was a really great talk. Thanks, Supriya. Really interesting. Yeah, thanks everybody for coming.
Thank you very much. Bye.